The purpose of this lab was to design our own experiment. I chose to model an inelastic collision between a cart moving at constant speed and another cart that was initially at rest. I analyzed the video and tracker to find the constant speed, and then, using that data, I modeled a collision in Python to find the change in momentum and the change in energy. The results of my lab were that the computational model predicted the motion of the video. The momentum was conserved during the collision because the change in momentum was 0, and the change in internal energy was 0.072 joules, so kinetic energy was lost during the collision. The momentum principle was used in the form delta P equals F net plus delta T because the speed of the cart was constant, and thus F net was 0. This means that delta P was also 0, so we can put the formula in the form m1v1 equals plus m2v2. Initially it was equal to m1 plus m2 was equal times the final velocity. The change in momentum should be 0 during this entire collision. The other fundamental principle used is the energy principle. The collision is inelastic. The carts stick together when they collide, so energy should not be conserved. This means that delta E is equal to work plus Q, where the kinetic energy final is not equal to the kinetic energy initial. Moving on to tracker, I uploaded the video of the inelastic collision from YouTube. I calibrated it, set up an axis where the carts moved in the positive x direction, and found the point mass of the first cart, the second cart, and when the two carts were attached. The top graphs represent the individual velocities for each cart. I checked these velocities for each cart and graphed them together so you can see where the collision took place and that the final velocity is slower than the initial velocity of the first cart. Notice cart 1 moves with a constant velocity and then slows down after the collision, and cart 2 is at rest and then gains velocity after the collision. In Python, I modeled two spheres on a track, one with constant velocity and one at rest. In order to do this, I set the initial conditions of the motion, the mass of the carts, 0.3 kilograms, and the initial positions, the initial velocities, and the kinetic energy before the collision. I then modeled the collisions and found the new positions. I found the total momentum and used it to find the new velocity. The bottom of this part of the code finds the final momentum and kinetic energy and the change in both of these. In the model, the sphere on the left has a constant velocity, and it moves with this velocity until it collides with the sphere at rest on the right. These two masses then move at a slower but constant velocity of 0.3795 meters per second when they are stuck together. With the data collected from Python, I calculated the initial kinetic energy of cart 1, 0.0216 joules, and the final kinetic energy of both the carts stuck together, 0.0108 joules. There is a loss in kinetic energy because the collision is inelastic. This collision is considered maximally inelastic because the two objects stuck together when they collided, and the change in kinetic energy was not 0. Initially, I said the change in energy was equal to the change in kinetic energy and internal energy only. But these values were not equal, so there must have been another source of energy included, which can be seen in the actual video where it is not shown in the computational model. The change in thermal energy is also at effect. There is a little friction between the carts in the real video and the track when the carts collided, which created thermal energy. All in all, the momentum of the collision was conserved and the kinetic energy was lost, just like was predicted.